Shown in the figure below are two point charges, Q1 and Q2, and the location of point P. All the locations, x, y in the figure are labeled in meters. Evaluate all the following. Part A, find the magnitude and direction of the electric field at the point P. And part B, what would be the magnitude of the force on a particle of charge Q equals 4 microcoulombs placed at the point P. The major feature that we need to recognize in this problem is that in order to find the total electric field at the point P, we're going to have to take a vector sum with two components. We'll have a contribution that I'll call E1 that comes from the positive 4 microcoulomb charge, and we'll also have a second contribution that I'll call E2 that comes from the minus charge. This problem is the first of several point problems in the review video set. The reason that I've chosen this one first is in fact that it's the most difficult. And what I mean by most difficult is I mean most detailed mathematically, so that the student will never be tempted to forget the fact that electric field is a vector, and in order to make the sum of E1 plus E2 we need to express both of these vectors in component format. Let's begin by learning a few things about the vector E1. Looking at the point P, I recognize that the electric field will point at this location away from any positive charge and towards any negative charge. The charge in question, the positive 4 microcoulombs, is down and to my left, and so for that reason the away direction will be up and to my right, meaning that E1 points in this manner. To assist in finding the size of E1, I'm going to draw a triangle, the hypotenuse of which is the line connecting my original charge of 4 microcoulombs to the point P, and the two legs are made so as to make a right triangle. We see by looking at the coordinates in the system that the vertical leg of this triangle must be 4 meters long, and the horizontal leg of this triangle must be 5 meters long. Because this is a right triangle, a squared plus b squared is c squared, meaning that the hypotenuse is going to be the square root of 5 squared plus 4 squared, or the hypotenuse has a length of square root of 41 meters. We have now collected all the information necessary to find the vector E1, both in terms of its x and in terms of its y component. But before we find the components, I'm going to find the magnitude. The magnitude of the electric field due to any point charge is the constant k, which takes the value 9 10 to the 9, times the amount of the charge. Since it's a magnitude, we will make the charge positive, 4 microcoulombs, divided by r squared, where r represents the distance from the point charge to the place where you're doing the location. That distance is square root of 41, and we need to remember to square that distance. Plugging in the numbers, we're going to find that the magnitude of this electric field is 878. In MKS units, this is either newtons per coulomb or volts per meter. Although later in the class I will prefer volts per meter, at the beginning we write newtons per coulomb. Clearly, in order to fully understand the vector E1, we're going to need to find both its horizontal component, E1 sub x, and its vertical component, E1 sub y. They make a triangle as shown by the purple arrows. And I'm going to label the angle theta 1 as occurring in this corner. You can see, based upon similar triangles, that the angle theta 1 also appears in the green triangle. At this point, you might be tempted to use an inverse tangent, an inverse sine, or an inverse cosine to find theta 1. I'm going to go a slightly different path. At the end of the day, what I would really like to know is what value does the cosine of theta 1 take, and what value does the sine of theta 1 take. These can be read off the diagram very simply, as we note that the cosine of theta 1 is 5 over the square root of 41, and the sine of theta 1 opposite over hypotenuse is 4 over the square root of 41. Armed with the magnitude, the cosine, and the sine, we are fully ready to calculate both the x and the y component of the vector E1. The table allows us to keep track of this calculation very carefully because we'll recognize that the x component of E1 is the magnitude of E1 times the cosine of theta 1, and the y component of E1 is again, E1's magnitude times the sine of theta 1. The magnitude is 878 newtons per coulomb in both cases, and on the left-hand side, we substitute for the cosine 5 over the square root of 41, and on the right-hand side, 4 over the square root of 41. Please note that because the vector E1 points to the right and up, both the x component and the y component are positive. If we complete the calculation, we get the following two values: positive 685.6 newtons per coulomb and positive 548.5 newtons per coulomb. We now return to the original diagram in order to complete the calculation in the same manner for E2. Because the second charge is negative, the electric field will point directly towards it. So from the point P, we point straight at the charge Q2. Again, we'll use a triangle so as to aid our calculation, where the hypotenuse is the line connecting the charge to the place where we're doing the calculation, and then the two sides are parallel to the x and y axis. You can see by looking at the coordinates for all of the points and charges that the vertical side is going to be of length 5 meters and the horizontal side is going to be of length 2 meters. This means that by the Pythagorean theorem we are able to calculate the hypotenuse as being the square root of 29 meters. Just as for E1, we're going to calculate magnitude, cosine, sine, and these will aid us in completing our table. The magnitude of E2 is the constant k times the amount of charge, which is 2 microcoulombs, divided by the distance of square root of 29 meters, quantity squared. This yields the result 620.69 newtons per coulomb. Again, we recognize in the figure that we're going to have to break this vector into a horizontal and a vertical component, and thereby define the angle theta 2 between the hypotenuse and the horizontal. That angle theta 2 is also found in the green triangle. By referencing the green triangle, we are able to calculate both the cosine and the sine of the angle theta 2. The cosine is adjacent over hypotenuse, and the sine is opposite over hypotenuse. Using these three results, we are then able to calculate the entries in our table for the vector E2. The x component of E2 will be its magnitude times the cosine of theta 2, and the y component of E2 will be its magnitude times the sine of the angle theta 2. Plugging in the values we had previously, we get the results as shown here. This time we need to take a little more care, however. We recognize that since the vector E2 points down and to the left, it will have negative x and y components. And when we plug in the values, we get the following results: negative 230 times 5 newtons per coulomb and negative 576.3 newtons per coulomb. Now we are finally ready to determine the vector E total in component format. To get the x coordinate, we simply add the two values in x, the positive 685 to the negative 230, and that gives us an answer of positive 455.1 newtons per coulomb. And performing exactly the same calculation in y, we find negative 27.8 newtons per coulomb. This is in fact an exactly correct result for the vector value of the total electric field. However, if we read the question carefully, we'll find that we were asked to find the magnitude and direction of the electric field. Therefore, in order to find the magnitude, we'll again need to refer to the Pythagorean theorem and put the x component in the first spot and the y component in the second spot. This yields a result for the magnitude of the total electric field at the point P being equal to 455.9 newtons per coulomb. Next, we need to solve for the direction of the total electric field vector, and we'll do that by taking the inverse tangent of the y component divided by the x component. This yields the result negative 3.5 degrees. We often need to take care as we do a calculation of the direction, because sometimes the inverse tangent will give us the wrong answer. It gives us the wrong answer whenever the x component is negative, and if that were the case, we must add 180 degrees. Here, because the x component for 55.1 was positive, we don't need to add the 180. We have now found both the magnitude and the direction of the electric field. To finish this problem out, we now need to find the magnitude and direction of the force on a particle of charge 4 microcoulombs placed at the point P. One option for approaching this calculation would be to do as much work as we just completed for the electric field. Find F1 with 2 components. Find F2 with 2 components. Add the components to get the components of the answer. Sum of the square, square root to get the magnitude, inverse tangent to get the direction, and that would be an awful lot of work. We're going to instead solve this problem by recognizing that the force is always equal to the amount of charge times the electric field into which you have placed it. Whenever the charge is positive, the force and the field are in the same direction. Whenever the charge is negative, the force and the field are in opposite directions. Because we have placed a positive 4 microcoulombs at the point P, we can say that the direction of the force is the same as the direction of the field, and that's negative 3.5 degrees. The only thing we need to add to this is to learn the magnitude of the force, and that will simply be Q times the magnitude of the field, or 4 microcoulombs times 455.9 newtons per coulomb. Plugging in the numbers and not forgetting about the micro unit on the coulomb, we'll find that the force is 0018 newtons, or 1.8 millinewtons.